In this video, we're going to talk about the dimension of a vector space. Now, we already have a rough idea of what that means for subspaces of Rn, but we can also define the notion of dimension for other vector spaces, like the vector space of polynomials. Now, before we define the dimension of a vector space, we need the following theorem. If a vector space V has a basis of n vectors, then every basis for V must have exactly n vectors. So no matter what basis you choose for your vector space, it will always have the same number of vectors. Now I won't go through the details of the proof of this theorem here, but essentially what you want to show is that if you have a basis with n vectors, then any set containing more than n vectors will be linearly dependent. Now let's define the dimension of a vector space. If V is spanned by a finite set of vectors, we say that V is finite dimensional. The dimension of V, denoted dim V, is the number of vectors in a basis for V. So this is why we needed our theorem. We needed to make sure that no matter what basis you picked, you always have the same number of vectors. And that's what we call the dimension of a vector space. Next, we say that the vector space consisting of only the zero vector has dimension 0. Lastly, a vector space that is not spanned by a finite set of vectors is infinite dimensional. Let's now look at some examples. Let's start with a vector space that we're familiar with, R2. Now the standard basis for R2 is the vector 1, 0, and 0, 1. Now since this basis has two vectors in it, we say that the dimension of R2 is 2. In general, if we have Rn, then the standard basis for Rn has n vectors. Therefore, the dimension of Rn is n. Let's now consider the vector space of polynomials of degree at most 2, which we'll call V2. Now V2 has basis 1t t squared. Since this basis has 3 vectors, we say that the dimension of V2 is 3. In general, if Vn is the vector space of polynomials of degree at most n, then Vn has basis 1, t, and so forth through t to the nth power. Therefore, the dimension of Vn is n plus 1, since there are n plus 1 vectors in the basis for Vn. Now, if we let V be the vector space of all polynomials, then V cannot be spanned by a finite set of vectors. To show this, we can do a proof by contradiction. Suppose that this vector space of all polynomials can be spanned by a finite set of vectors. Then in this finite set of vectors, there has to be a vector that has the highest degree. So let's say that vector has degree k. Then the polynomial t to the k plus 1 is not in that span of vectors. So t to the k plus 1 is a vector in V, but is not spanned by those vectors, which means that we have a contradiction. So V cannot be spanned by a finite set of vectors. Therefore, we say that the vector space of all polynomials is infinite dimensional. Let's look at a few more examples. In this example, we have H a subset of R4, consisting of vectors of the form a minus 2b plus c, 2a minus b plus 5c, negative a plus 3b, and b plus c, where a, b, c are real numbers. We're asked to find the dimension of H. If I want to find the dimension of H, I'll need to know how many vectors are in a basis for H. Let's start by describing H as a span of vectors. Vectors in H are of the form a minus 2b plus c, 2a minus b plus 5c, negative a plus 3b, and b plus c. So what we're going to do is take a vector that looks like this and break it apart. I'm going to separate the vector into 3 parts. A vector with the a terms, a vector with the b terms, and a vector with the c terms. So I have the sum of the vectors a, 2a, negative a, 0, plus negative 2b, negative b, 3b, and b, plus c, 5c, 0, and c. Factoring out the a from the first vector, I have a times 1, 2, negative 1, 0, plus, factoring the b out of the second vector, we have b times negative 2, negative 1, 3, 1, plus, factoring the c out, we have c times the vector 1, 5, 0, 1. Since a, b, and c are any real numbers, we see that H is the set of all linear combinations of the vectors 1, 2, negative 1, 0, negative 2, negative 1, 3, 1, and 1, 5, 0, 1. So h is the span of those three vectors. But this doesn't allow me to conclude that the dimension of h is 3. We need to know if these three vectors form a basis for h. So what we need to do is check if these vectors are linearly independent. And if there is some dependence between them, I need to remove vectors that can be written as a linear combination of the others. The process for doing this is identical to what we did to find the basis for the column space of a matrix. So we'll put these vectors into a matrix and row reduce it. And that's going to reveal to us if there's any relationships between the vectors. So I have the matrix 1, negative 2, 1, 2, negative 1, 5, negative 1, 3, 0, 0, 1, 1. Now I won't go through the details of row reducing this, but what you should end up with is the matrix 1, 0, 3, 0, 1, 1, 0, 0, 0, 0, 0, 0. Now, since the first two columns are pivot columns, we know that those two vectors are linearly independent with each other. The third column is not a pivot column, so there's some dependence there. Looking at the columns of the row-reduced matrix, we see that the third column is 3 times the first column plus 1 times the second column. So those relationships hold with our original vectors, which means we're going to remove the third vector from our list, and that's going to form our basis for h. Basis for h is the set 1, 2, negative 1, 0, and negative 2, negative 1, 3, 1. Since there are two vectors in my basis, I can conclude that the dimension of h is 2. So again, I want to mention that even if you can describe your subspace as a span of a collection of vectors, that's not going to immediately tell you what the dimension of that subspace is. You need to find a basis for that subspace, then count the number of vectors in that basis. So now let's look at a few more examples. Let A be an m by n matrix. What is the dimension of the column space of A? Now let's think back to how we found the basis for the column space. In general, the column space of a matrix is the span of each of the column vectors. But there might be some linear dependence there. So what we did was we row reduced it, and in the end, the vectors that corresponded with the pivot columns were a basis for the column space of A. So whenever I have an m by n matrix, the dimension of the column space is the number of pivot columns of that matrix. So now, what about the dimension of the null space? To find the basis for the null space of a matrix, we want to solve the homogeneous equation A times x equals the 0 vector. After row reducing our matrix, we write our solution in parametric vector form. And the vectors that we see are a basis for the null space of A. Now, how many vectors do we have? Well, we have one vector for each free variable. So the dimension of the null space of A is the number of free variables I'll have after row reducing our matrix. Or we can think about this as the number of non-pivot columns that we have in the matrix. Before I end this video, I want to mention a couple of theorems. First, let H be a subspace of a finite dimensional vector space V. Then, the dimension of H is always less than or equal to the dimension of V. This theorem should make sense geometrically. For example, if I have a two-dimensional vector space, a subspace of it can't be three-dimensional. In general, your subspace can't have dimension that exceeds the dimension of your vector space. The second theorem that I want to mention is called the basis theorem. The theorem states that if V is an n-dimensional vector space, first, any linearly independent set of n vectors is automatically a basis for V. So normally, if I want to check that a set is a basis for a vector space, it needs to satisfy two conditions. The set needs to be linearly independent, and the set needs to span your vector space. So the first part of the theorem tells me that if I have a linearly independent set of n vectors, then I don't need to check that they span my vector space. I know that that's going to happen automatically. The second part of the theorem says that if I have a set of n vectors that span my vector space V, then it's automatically a basis for V. So any set of n vectors that span the entire vector space will automatically be linearly independent, and I don't need to check that condition. So this theorem is useful if I know that I have an n-dimensional vector space and I have a collection of n vectors. If they're linearly independent, they're going to form a basis. Or if they span my space, they're going to form a basis. So that's it for this video. In our next videos, we'll talk about the row space of a matrix and also talk about the dimensions of various subspaces associated with matrices.